Hi, everybody. Here we are for our pre-lab for our first session of CHY 116, the kinetics of fading indicators. I'm not sure where exactly you are at with your knowledge of kinetics from lecture. I haven't had a chance yet to take a peek at Dr. Benedict's schedule, so I don't know exactly what you've covered and what you haven't. So I'll try to fill in the gaps a little bit, but some of this may seem a little bit over your head until you do get a little bit deeper into lecture as well. And so very basically, the study of kinetics in general is the study of the speed at which chemical reactions take place, which can be some very powerful information depending on the reactions that we're looking at. As you'll see, not so much in this lab, but in our second kinetics lab, and as you'll talk about a little bit more when you get deeper into this in lecture, something else that kinetics can tell us or give us hints about is the mechanism of a chemical reaction. One of the things that we sort of gloss over when we talk about chemical reactions, we talk about A plus B makes C, boom, and that's sort of it. What we don't necessarily discuss in those preliminary talks about reactions are what's taking place within that arrow. Is it maybe a two-step reaction that A plus B makes some sort of D intermediate that then reacts with another A molecule in order to go make C, something like that. And looking at kinetics can start to give us some clues about some of that as to what exactly sort of is happening within that space that we just designate with an arrow in the chemical reaction or chemical equation. What's actually happening in that arrow to make the equation happen or make the reaction occur. And that's some of the things that the study of kinetics can start to give us some clues about. And so it's a very, very important branch or topic in chemistry in general. It can give us a lot of very important information. Now, if we think about the speed of chemical reactions in general, then we start to think about, well, what sorts of things can affect the actual rate of a reaction? And so when we're thinking about that rate, we're thinking about that speed of a reaction, there are really a couple main things that can drive that. One of those is the concentration of the reactants. And so if we think about what has to happen for a reaction to occur, if we've got maybe simply just A plus B making C, then in order for this reaction to happen, A and B have to be able to meet up with each other in whatever reaction, whatever our medium is, right, wherever we're running this reaction. But A and B have to be able to meet up with each other, have to be able to meet each other in order to react, meet each other with enough energy in order for the reaction to occur. And so the concentration can definitely play a huge role in that. The more of A and B that you have, the more likely these collisions can actually occur, which would speed up the reaction. There are a few nuances there, which again, you'll definitely be learning about and talking about a little bit more in lecture, and we'll see a little bit of that here. But that is absolutely something that can definitely affect the speed of that reaction, is how much of the reactant is there. The other thing that can affect the speed of a reaction, again, because the reactants have to not only meet, they have to meet with enough energy for the reaction to occur. And sorry, I always forget about this little thing that shows up due to QuickTime. Maybe that'll disappear here in a second. There we go. And so the higher the temperature is, usually, the more active the molecules are, the more energy the molecules have, and the higher percentage of those collisions will have enough energy for the reaction to occur. So temperature can absolutely play a big role in the speed of a chemical reaction as well. Now, as far as our experiment, what we're doing here with the kinetics of fading indicators, we're not going to really worry about temperature because everything that we're running is going to be at room temperature. And so that's not going to play a role in what we are looking at. And so we're going to be really zeroing in here on our concentration of our reactants. In order to go through our study of kinetics with this lab, the kinetics of fading indicators, we're going to take a look at an indicator that you've probably all seen at one point or another. You didn't see it, actually, you didn't see it in 114. We're going to use a chemical known as phenylphthalein, which if you've ever done some acid-base titration in any other chemistry class or any other course, It's that classic pink color that you see in a titration. And so you may have seen this or you may not have. And we're just going to abbreviate phenylphthalein as P2 minus. There's a good illustration of it in your lab manual. If you take a look on page, where'd it go here? On page 2, there's a good drawing of phenylphthalein and what it looks like and sort of what's going on with the reaction that we're going to talk about here in just a second. But phenylphthalein itself is pink. And we're going to react that just with some base, react that with some hydroxide, some OH minus. And that goes on to create what we call the phenylphthalein hydroxide complex. We're not going to worry about too much about the charges. We'll just put them in there for accuracy's sake. But this complex is now colorless. And so what we can do, since we start from something, our initial reaction, we start with something pink, and we go to colorless, we can monitor this disappearance of the color in order to judge the speed of our reaction. And so let's say that again, because that is important. Essentially what we are doing is monitoring the disappearance of color in order to gauge the reaction speed. And so a faster reaction, we would see a faster disappearance of color. Stands to reason. And so that's really what we're investigating here. And so that is our basic reaction. Just redraw that up here, our phenylphthalein plus our OH minus, creating our phenylphthalein hydroxide complex. And so what we're going to try to find here, and this is where I don't know if you've really covered this much in lecture yet, you might have just started to hit on it. But what we want to try to find for this reaction is what we call the rate law of the reaction. In very general terms, the rate law for this reaction would be that the rate is going to equal K, lowercase k, very, very important. When you get to equilibrium, you're going to be working with uppercase K, so don't confuse the two. This rate constant is a lowercase k. That is important to make that distinction. But that lowercase k is what we call the rate constant. And rate constants are different for every reaction. And so that's one of the things that you're hopefully going to be finding in this experiment is what the actual numerical value is for the rate constant for this reaction. But it's K times the concentration of each of our reactants raised to some power. And we're just going to abbreviate though, or put in N and M for our what we call the orders. And so that power is the order of the reaction with respect to that certain, with respect to that reactant. And so if N, for instance, is 0, then we would say that this reaction is 0 order with respect to phenylphthalein. If N is 1, then this reaction is first order with respect to phenylphthalein. If M is 1, same thing, we would say this reaction is first order with respect to hydroxide. And then you can add up the orders to find the overall rate order for the entire reaction. Again, some of that might make a lot more sense when you get deeper into things in the lecture. We're not going to get too deep into it here, except again, to just sort of note that this is really what we're looking for, and what we're trying to find for this reaction is we're trying to find the rate law, which means that we need to find our actual values for K, N, and M, so we can have our full rate law for this particular reaction. Now, there are two basic ways that you go about finding, there are two basic ways that you can go about finding this information for any sort of reaction. One of those is what I would call sort of a classic kinetics experiment, in which, again, here's our equation that we're looking at. It's sort of a classic kinetics experiment. What you would do is you would set up some different trials, And in those different trials, you would have differing concentrations of your phenylphthalein and your OH minus, and you would measure the actual rate. Rate, by the way, if you haven't seen this, is typically measured in molarity per second. So how much does the concentration change as a function of time? And so what you might do with something like this is maybe set up your first trial with 0.1 molar for each. And you would find the rate, whatever that rate happened to be. You would find a way to measure that change in molarity over time. And then you would change one of those and keep the other the same, find the rate. Then maybe a third trial where you change the other and keep it the same and find the rate. And in this way, you would be able to take a look and see. So again, keeping in mind that your goal is to find that rate law. Oops, I think that was an N, wasn't it? N. And so keeping in mind our goal is to find these orders and this K value. If you set up an experiment like this, then okay, you can compare these two experiments to see what changing phenylphthalein, what effect that has on your rate. And you would then compare 1 and 3 to see what effect changing the OH minus has on the rate. And in that way, you would be able to then tease out your values of K, N, and M. This method, however, relies on being able to definitely calculate this rate value. So you would need to be able to measure actual numbers to put in here. So that means that you have to definitely be able to measure the molarity of something. And we'll talk about that a little bit more in our next experiment, because this, in fact, is exactly the way that we're going to go about experiment 2. This is our iodine clock lab right here. We can't do that with our experiment because we don't have good ways to actually be able to measure the molarity accurately in order to get real rates here. So we can't do this sort of what I would call, again, sort of the classic kinetics table in order to find rate for our particular reaction. What we can do, however, is look at some graphing and some math manipulation. Now, don't worry about the origins of this, but it turns out that if you're looking to find that order, you're looking to find that exponent for any reactant within a reaction, we can graph some of that data. And so, for instance, if you graph, in our case, the concentration, if you take a graph of your concentration over time, if that graph is linear, then that means you have what we would call a zero order reaction. So the order with respect to that reactant would be 0. So again, maybe in our just sort of classic A plus B goes to C. If we take a graph of the concentration of A over time, and that's linear, then that means that the reaction would be called 0 order with respect to A. And the slope of this line equals our negative K value in our rate law. And so that's, again, if it's linear. If, however, the graph of the natural log of the concentration versus time, if that is linear, that means we have what we call a first order reaction. And the slope equals, again, the negative K value. Lastly, if you graph 1 over the concentration of A versus time, and you get a graph that's linear, then that would be a second order reaction with the slope equal to K. And so this means that what we can do is, if we are able to sort of isolate one reactant, we can create these 3 graphs. If we're able to measure the concentration of that reactant over time, then we can do a graph. We can do this graph of just the concentration versus time. a graph of the natural log of the concentration over time, or 1 over the concentration versus time, whichever one of those is linear, that tells us what that order of the reaction is, tells us that exponent value. And so this is in fact what we're going to do for this lab. And we'll take a look at how we're doing that in just a second. But that is basically what we are going to do, is to do some graphing to find out the order of the reaction with respect to at least one of our reactants. And we'll talk about what that means in just a second. Because really only one of these graphs, or one of these graphs, will be more linear than the others. And so that tells you what the order will be. Now we do have an issue in this lab. Again, sort of putting our overall, what we're shooting for here. So here's our reaction, our P2 minus plus our OH minus. All right, let's just, this is messy. Let's start this one over, shall we? So here's our overall reaction. Here's the rate law that we're looking to try to find. And ultimately, we're trying to find our K, N, and M values. Now, we just talked about how we can take some graphs of the concentration in order to find out the order. But we have 2 different reactants in this experiment. And so what we're going to do is something that we call a pseudo rate law. In this experimental design, we have a lot of OH minus. Our concentration of OH minus basically floods out what the P2 minus is. So there's a lot more of this OH minus in our reaction than there is phenylphthalein, for a couple of reasons. One is that makes sure that we definitely use up all the phenylphthalein, so that we go completely colorless by the time the reaction ends. The other thing that does for us is, since there is so much of this compared to this, that essentially keeps the OH minus constant throughout this reaction. What that means is that we can reduce this rate law to what we call a pseudo rate law, in which we're going to say that the rate equals, we're going to call this K1 instead, of just the phenylphthalein, where now K1 incorporates the real rate constant, K, and the OH minus concentration. And we'll see where that all fits in sort of as we get going a little bit. But so what we can do then, that leaves us with a way to devise an experiment in which now we're only concerned about the concentration of one of the reactants. And this K1 wraps all of that in. And we'll talk about how we then get from the K1 to the real K that we're actually looking for. But this gives us a way to just worry about one reactant. And so it does leave us with a way, or with a need though, to be able to find the concentration of the P2 minus. The way that we're going to find the concentration of the P2 minus, so we need to know our concentration then of the phenylphthalein. And so the way we're going to do that is remember Beer's law. Hopefully you remember this from 114. And so Beer's law, absorbance equals our molar absorptivity coefficient times our path length times our concentration. And so it's kind of similar to when we did this in 114. So we're measuring absorbance. We're measuring how much light is absorbed by the sample. As a quick little recap, what that looks like is you've got a cuvette here. Here's a light source. And so light is going to pass through. Here's your phenylphthalein solution. So our phenylphthalein is in there. Light passes through. So some of the light passes through to the detector. And so the amount of light that passes through is going to be dependent on what the concentration is of your sample. The more sample that you have in here, the more light gets absorbed by this sample, and the less that actually reaches the detector. And that's what this is all about. The absorbance, how much light is absorbed, is a function of this molar absorptivity thing, which we're not going to really worry about for our purposes. It's a physical constant that does apply to solutions. Your path length here is literally how far is the path length that the light is traveling through the solution. But then the kicker, the important part, is this concentration. And so what this really tells us, and what we really have to take home from this, is that absorbance is directly proportional to our concentration. And so what this means, the way that we can use this, is it's really tough for us to measure the actual concentration of phenylphthalein. This tells us that we don't have to, because this tells us that if we measure a decrease in absorbance, that is functionally equivalent to measuring a decrease in the concentration. And so that, in fact, is what we are going to do for this experiment, is measure the absorbance over time. And we're just going to plot that the same way that we would have plotted concentration. So you're going to take some plots of absorbance versus time, a plot of the natural log of absorbance versus time, and a plot of 1 over the absorbance versus time, and look to see which of those is linear. Now again, whichever one of those is linear tells you if our order with respect to phenylphthalein is going to be 0, first, or second. But we can use absorbance rather than using concentration. And that's exactly what we do in this experiment, is we set up several solutions in which we then measure we start the experiment, and then at certain time points, we simply measure what the absorbance is. And in all of them, the absorbance goes down over time because the reaction is just occurring. We have less and less of the phenylphthalein in there because more of it's reacting. So remember that phenylphthalein is that pink color. So just as a reminder so we have our P2 minus plus our OH minus. So remembering that this here is pink and this is colorless. And so what we're really measuring over time is the disappearance of that pink color, because that's what's absorbing. That's what's actually absorbing the light, is the phenylphthalein, the pink color. Over time, that disappears as it reacts with OH minus to become colorless. And so that's what our data plots. And so using that information and looking at which one of these graphs is linear, that's going to then be able to give us, we go back to here, boom, that's going to then be able to give us our N value, tell us what the order is with respect to phenylphthalein. So now we would have the order with respect to phenylphthalein. And so once that is known, once this is known, and this is where I definitely don't want you to get bogged down in the math. But now once that is known, once we know that order with respect to phenylphthalein, we can start to play with a lot of, for lack of a better word, a lot of fancy logarithmic math and a lot of fancy graphing and log math that will lead us eventually to the order with respect to hydroxide, and then would lead us to the actual K value rather than the K1 value. And that's where like I said, I really don't want you to get bogged down in that. That's some fairly heavy log math and some fairly sort of deep analysis that goes beyond what I want you to worry about. So just sort of trust me that the rest of the analysis, and I'm going to show you how to run through a lot of that analysis with a pretty fancy spreadsheet that one of our instructors put together. But we'll be able to get there. To me, what the really important thing is in this lab is really recognizing this aspect right here. That this is one of the ways that we can identify the reaction order of a particular reactant is by looking at graphs of the absorbance or concentration, but the absorbance over time, the natural log of absorbance over time, or 1 over absorbance versus time, because that will tell you whichever one of those is linear, tells you if it is 0 order, 1st order, or 2nd order. To me, that's sort of the heart and the important take home from this lab conceptually, is using those graphing techniques in order to really find the order of a reaction. And then the rest of it ends up being some pretty fancy log math that you can use to find everything else that you're going to need. And so let's take a look at how you're actually going to do this. Like I said, one of our instructors, Professor Ambrose, set up what I feel is a really great worksheet to help guide you through all this analysis. So if you start looking on page 7 of, oh, sorry, let me back up. And so we're not going to do this with just one solution, just to make sure that everything is the same amongst different concentrations. We're running 6 different solutions that all have different starting molarities of phenylphthalein. And so we need to be able then to analyze all 6 of those solutions and look for those graphs the way we were just talking about. And so this is your overall data. This is the data that was collected. This is the same data that's posted on the website. We just populated it into this spreadsheet for you already. Now let's look at a few of the different ways you're going to use this. And I'll be showing you just a few different Excel tricks with this too. This is a very Excel heavy lab, and it's a good lab to hone your Excel skills, but I'm going to show you a few of the things that you can do. So again, remembering that, so this is our raw data for each solution. So these are the absorbance values over time for each solution that you have. So here's just our raw data. And what we really want to do, and I'll just tell you flat out, this is not 0 order. And so we want to discover, once again, remember, what we want to find out first is when we're looking at our overall equation. So our phenylphthalein plus our OH minus. We've got our rate law. And so the first thing that we're really trying to key in on is to try to find that order there, to try to find that N value. And so in order to do that, and that's either, we know that it's either a 1st or 2nd with respect to the phenylphthalein. If it is 1st, then that means a graph of the natural log of absorbance over time will be linear. If it is 2nd, then a graph of 1 over absorbance versus time will be linear. And so that's the first thing that we need to find out. And so we have our data here. And so table 2, what we need to do is find the natural log of all of these values. And so to show you the quick and easy way to do this in Excel, so remember, Excel will do the calculation for you. And so we want to do equals, there we go, equals natural log, which is ln, and then parenthesis. So you see here, I'm at times 0 of solution 1, times 0 of solution 1. Here's my absorbance value. So I'm just going to click on B5. So now it's going to take the natural log for me of whatever is in this cell. And I'm going to hit enter, and there's my number. I'm not going to worry about what the number is. That's really not important. We're going to use that in a little bit. But then watch this. What I can do here, if you haven't seen this in Excel, and Google Sheets is similar, but you see that little square down there, right in the right-hand corner, lower right-hand corner? If I grab that and I drag that over to the rest of these cells, it's going to copy that equation for me into all of these cells, but using the appropriate cell from my initial data. So you see this. So now if I click on this, you see what it does. It's the natural log of F5. So this slot here is the natural log of this, which is exactly what I want. So that's perfect. Now what I can do is I can highlight all of these, click on this arrow here and drag down, and boom. So now what I have in this table here is the natural log of all of these values. And so again, remembering that what I want ultimately is to be able to compare these two graphs. So we're working on this one right now. I want to be able to compare those two graphs, see which one is linear. And so we're using 6 different solutions for this. So what you really have to do is we're going to look at each of these graphs. We're going to graph this one here versus time. And so we want this graph. We want this graph versus time, and so on. So that we can then look at the slopes and the R² values for each of those lines. Because remember, the R² value, remembering back to 114, your R² value is what's going to tell you how close to linear that graph is. Closer that value is to 1, the more linear it is. And so what you want to do at this point is you need to make all these graphs, all these 6 graphs of each of these solutions versus time. And you can plot them all onto one graph. Easy way to do that is if I highlight the whole thing. You don't want to highlight the headings here. That will mess your graph up. Just highlight the values. So I've got all the values highlighted here. And I'm going to insert chart XY plot. And you can see now here what I have. Blow this up to make it a little easier to see. So I've got all 6. So I've got 1, 2, 3, 4, 5, 6 graphs here that are all just solutions 1 through 6 on the y-axis here versus time here on my x-axis. And so you're going to do that same thing for also the inverse, for the one over absorbance versus time. But then you're going to need to be able to start to compare what those slopes and R² values are. And so what I would do here, so here's where we're going to pull out the slope and the R² value for each different solution. And these aren't necessarily in order of, they don't necessarily go from 1, 2, 3, 4, 5, 6. So that makes it a little bit more difficult. To me, what I found the easiest thing to do here is if you click on one of the graphs, so you can see I've clicked on one of the plots here, one of the lines, and we can see that this top line is actually solution 3. So I know that this line is solution 3. I'm going to right click to add my trend line. And with my trend line, I want my equation and my R² value. And so I can see what that is here. I'm just pulling it up so I can actually see it. And so it was solution 3. And so my slope, you can see here. Let's blow this up a little bit so you can actually read it. So again, this was solution 3. So I know my slope is 0.0495, negative 0.0495. So negative 0.0495. And I see my R² value is 0.9662. And so now you would go through and do that for the rest of them. I click on this one here. I see it's solution 6. I would add my trend line, include my R² and my equation so that I can put in my slope and my R² for solution 6. And so you're going to do that with all 6 of these. You're then going to do the same exact thing here, but now it's your inverse of absorbance versus time, your inverse of the absorbance versus time. So same idea. I'm going to do equals 1 over, and then back to my original data sheet. I'm just going to move this down out of my way. I got to move this out of my way first. Oop, there we go. Oh, maybe not. Okay, get out of my way. There it goes. Let's try that again. So equals 1 over, back to my initial data sheet, hit enter. So there it is. And then I can go through the same exact thing. I can fill over, and I can fill down, populates my entire graph with 1 over the absorbance for me. And then you would do the same thing. You would go ahead and get do your entire graph, all 6 of your graphs for this, and use your trend line and to find for each to find your slope and your R squared. And then what you'll see next, and that's as you input into your graphs, into your tables down here, it's going to then populate your R squared values for you here. And so this is going to find, once you have all 6 of these, this is going to calculate your average R squared. And so you'll have your average R squared of your natural log of absorbance versus time, and your average R squared of your 1 over absorbance versus time. Now remember that R squared, the closer R squared is to 1, the more linear that graph is. And so whichever one of these ends up having an average closest to 1, that's the one that's more linear. And so let's say, for instance, after you go through all of that with both of these graphs, you find that it's this graph 1 here, that this average value right here is closer to 1 than this one is, then that tells you that what we are dealing with is this situation right here, where we have phenylphthalein. Again, if that occurs, if you find that that one is the more linear curve for all 6 solutions, then that tells you that the reaction with respect to phenylphthalein is first order. And that basically takes you through page 7 of your analysis in the post lab. Now on page 8, for the rest of the analysis, you would start to go through and simply populate and fill out the rest of our table here. And so the rest of this section right here walks you through exactly sort of what I just talked about. A graph that has a stronger correlation determines the reaction order and so forth. The rest of this starts walking you through the rest of your analysis for page 8 to try to find the order with respect to the OH minus, and then find the actual K value, not the K1 value, not that pseudo value. And so that's what the rest of this is. And so as you work through your post lab on page 8, this is what's going to be able to get you to that analysis. And I'm going to email this spreadsheet to you as well, so that you can absolutely use this exact spreadsheet as you are working. And so that should really help with all of your analysis and with trying to put all this together, hopefully make a little bit of sense. Now, like I said, as you're going through, especially that on page 8, and you're going through the rest of this, don't get lost in the weeds. Don't get lost in that math. Don't necessarily worry about what the logs are all about. Just know that the log math of it works out, and that this spreadsheet is all set up to just help you with the graphing and all that spreadsheet analysis that you have to do for the rest of that analysis on page 8. So hopefully this should make it a little bit easier for you than just working through it on your own with your own spreadsheets. And so then ultimately, by the very end, what you should be able to have is finally your rate equation for this particular reaction. But now you'll have actual values for K, M, and N. And once those values are in there, then that is the actual rate law for this reaction. I know, it's a mouthful and that's a lot. The other thing that I would caution you on this lab, I mean, in general, this lab is a math heavy and a graphing and spreadsheet analysis heavy lab. there's a lot here, and this is a lot of work. I don't want you to necessarily get frustrated with a lack of understanding. Some of this is going to be a little bit over your heads for now. I'll be honest about that, especially until you get a little bit deeper into kinetics in lecture, and until kinetics starts to make a little more sense to you. Some of this is going to be going over your head. So again, the things that I really want you to focus on are sort of that we are using technique number 2 when we look at kinetics in general. We're using technique number 2, in which we graph we graph various things about concentration as a function of time, either just the concentration over time, the natural log of the concentration over time, or 1 over the concentration versus time. And whichever one of those is more linear will tell us what the reaction order is. Again, to me, that's really the meat and the important part of this lab, is really focusing in on that idea of that's one of the ways that we can narrow in on some of that kinetics data. We can then use that and some fancy log math to get the rest of the information that we need. And that's a lot of what this spreadsheet and what this analysis walks you through, is some of that fancy math, and that's some of that fancy log math. And so don't get frustrated and upset if you don't understand that. It is some pretty complicated stuff. Just trust us when we say that this math works out, and that the spreadsheet will guide you through it so that you're able to get to this rate law. And so if you have questions as you're going through this, as always, do not hesitate to email me. If we take a look back at the website, by the way, so that's how you're going to do all of your analysis, but there's the experimentation part as well, which unfortunately you will not be there to do. But if you go to the website, you go to the experimental pages, the kinetics of fading indicators, you'll see here a series of experimental videos. We have about a little under an hour total. And these are all videos of Professor Tracy conducting the experiment. And he conducted this when we first went remote for the pandemic 2 springs ago now, I guess. He did this for the summer because we were still there. Anyway, when we first went remote, Dr. Tracy had recorded himself performing most of the procedures for 116. And so for your notebook, for the time that you normally would be in lab doing this, that unfortunately we can't be there for, what I want you to do is to watch these videos and record in your notebook as if you were doing the experiment yourself. And so everything that he is doing, record that in your notebooks as if you are doing it, as if you are right there with him performing the experiment, as if you are his lab part, or as if you are him and actually doing this. And so each of these 4 different parts, and so documenting everything that is going on. Don't worry for this lab. Don't worry about writing the data down in your lab notebooks. I'm personally not going to worry about that for this one. So you've got the data here, and this data is already populated into the spreadsheet that I sent you as well, and that will be linked up on the website. You will also see, and I don't have them there yet, but I will have shortly after this video is done, I'll have some of the different spreadsheets and whatnot right in here too. So just come to my instructor page, and you'll see the links to the Excel worksheet that I'm going to send you as well. But that's where you will go for the actual experiment itself. And again, writing down in your notebook as if you were doing it along with Dr. Tracy. And so to recap, so rather than be in lab, which unfortunately we cannot be, you are going to watch these videos here and record in your notebooks as if you were actually doing the lab, and then work through this Excel worksheet that Professor Ambrose put together. Very, very good spreadsheet. I like this a lot. I'm going to continue using it. And so work through this in order to find first your reaction order with respect to phenylphthalein. And then the rest of it works you through finding the reaction order with respect to hydroxide. And then finally, the rate constant for the reaction. Those 3 components then get you to the rate law for this reaction, which is what we're looking for. So that is it. At this point, if I were you, I would probably go ahead and watch those videos and write in your lab notebooks as if you're doing it. You know, because that's what we would do if you were actually there. Is when I was done, when I would finish my pre-lab, that's when you would jump in and actually start doing the lab. And so that would be my advice to you, would be to start watching those videos and then going through and then writing your notebooks, and then hopefully going right into doing your analysis. And if you do have any questions as you are working, please do not hesitate to email me. Definitely email me, and I can try to work you through any issues that you're having. And remember as well that when you are turning this material in, I don't have it up anymore, but I can bring it up real quick. Let me just bring up my Google Classroom. So it takes me a second to get there. Internet's slow at home today. Switch it to a student view. And so when you are done, you'll submit everything via Google Classroom. And so as far as due dates for experiment 1, the kinetics of fading indicators, your notebook and your post lab are due February 3rd. Hopefully I'll be seeing you in class on that day, right in the lab. How about February 3rd? Sorry, that is a mistake. Because I believe I see you on Mondays, don't I? Thought you were my Thursday section, but you are not. I see you on Mondays, so I'm going to fix that. I will do so right now. That is going to be due on, why don't I fix it while you're watching? You'll get the joy of watching me adjust this. If it'll let, I guess it's not, well, it's not letting me from here because this is me in the classroom mode. But so that's not February 3rd. I'm going to fix that. That is going to be due by January 31st, 1 week from, and that's typically how things will go. You'll have 1 week after we do the lab in order to submit your notebook and your post lab. And so your notebook and your post lab from this first lab, the kinetics of fading indicators, due by January 31st at 12:30, basically due before you come to lab. And so that is it. If you have any questions, don't hesitate to send me an email and we'll see what we can do for you. Have a good day.